how do we state the issue of normalization? See, the spherical harmonics are functions of theta and phi. So what it makes sense is that you would integrate over theta and phi, solid angle. The solid angle is the natural integration. And it's a helpful integration because if you have solid angle integrals and then radial integrals, you will have integrated over all volume. So for the spherical harmonic, solid angle is the right variable. And you may remember, if you have solid angle, you have to integrate over theta and phi. So solid angle, you think of it with a radius of 1. Here is sine theta. So what is solid angle? It's really the area on a sphere of radius 1. The definition of solid angle is area over radius squared, the part of the solid angle that you have. If you're working on a sphere of radius 1, is the area element is the solid angle. So the area element in here would be, or the integral over solid angle, this is solid angle, the omega. You would integrate from theta equals 0 to theta equals pi of sine theta d theta. And then you would integrate from 0 to 2 pi of d phi. Now, you've seen that this equation that began as a differential equation for functions of theta ended up being a differential equation for a function of cosine theta. Cosine theta was the right variable. Well, here it is as well, and you should always recognize that. This is minus d of cosine theta. And here, you would be integrating from cosine theta equals 1 to minus 1. But the minus and the order of integration can be reversed, so you have the integral from minus 1 to 1 of d cos theta, and then the integral from 0 to 2 pi of d phi. So this is the solid angle integral. You integrate d of cosine theta from minus 1 to 1 and 0 to 2 pi of d phi. And we will many times use this notation, the omega, to represent that integral so that we don't have to write it. When we have to write it, we typically prefer to write it this way so that the integrals should be doable in terms of cosine theta. So what does this all mean for our spherical harmonics? Well, our spherical harmonics turned out to be eigenfunctions of Hermitian operators, and if they have different L's and M's, they are having different eigenvalues. So eigenfunctions of Hermitian operators with different eigenvalues have to be orthogonal. So we'll write the main property, which is the integral of 2 L, say L prime, M prime of theta and phi. And you'll put the star here. Well, I'll put the star just on the y. It means complex conjugate of the whole thing. Remember, in an inner product, one-way function goes complex conjugate. the other wave function is not convex conjugate. There are different ones because L and M and L prime and M prime could be different. So orthogonality is guaranteed. Two different ones with different L's and different M's should give you different values of this integral. So at this moment, you should get a delta L prime L, delta M prime M. And if L and M are the same as L prime and N prime, you have the same spherical harmonic. And all this tremendous formula over there with 2L plus 1 and all these factors guarantee that in that case you get 1 here. So this formula is correct as written. That is the orthonormality of this solution. Probably at this stage it might be a little vague for you. We saw this long time ago. You may want to review why eigenfunctions of Hermitian operators with different eigenvalues are orthogonal. And see if could you prove it? Can you do it, or is it kind of a little fuzzy already? We saw it over a month ago. So, time to go back to the Schrödinger equation. So for that, we remember what we have. We have minus h squared over 2m Laplacian of psi plus v of r psi equal e psi. And the Laplacian has this form so that we can write it the following way. Minus h squared over 2m 1 over r the second the r squared r psi. Let me write it. Well, I won't close the bracket here. Minus, minus this term. So I'll write it minus 1 over h squared r squared L squared psi plus v of r psi is equal to e psi. Now, you could be a little concerned, we're doing operators, and you say, well, am I sure this L squared is to the right of the R squared, R and L has momenta don't commute with R, maybe there's a problem there. But rest assured, there's no problem whatsoever. I realized that L squared was all these things with dd thetas and dd phis. There was no R in there. It commutes with it. There's no ambiguity. We can prove directly that L squared commutes with R, and it takes a little more work, but you've seen what L squared is. It's a dd thetas and dd phis. It just doesn't have anything to do with it. Okay, so now for the great simplification. You don't want angular variables in this equation. You want to reduce it to a radial equation. So we try a factorized solution. Psi is going to be of all the coordinates is going to be a product of a purely radial wave function of some energy E times a YLM of theta and phi. And we can declare success if we can get from this differential equation now a radial differential equation. Just for r. Forget thetas and phi. All that must have been taken care by the angular momentum operators. And we have hope for that. In fact, if you look at it, you realize that we've succeeded. Why? The right-hand side will have a factor of YLM untouched. V of r times psi will have a factor of YLM untouched. This term, having just r derivatives, will have some things acting on this capital R and YLM untouched. The only problem is this one. But L squared on YLMs is a number times YLM. It's one of our eigenstates. Therefore, the YLMs drop out completely from this equation. And what do we get? Well, we get minus h squared over 2m, 1 over r, d second dr squared, r, capital R-E, minus L squared on psi ln, or YLM now, is h squared times L plus 1. So the h squared cancel, get L times L plus 1, r squared, and then we get the R E of r times the psi ln that has already, I started to cancel it from the whole equation. Yeah. So I use here that L squared from the top blackboard over there has that eigenvalue, and the psi ln has dropped out. Then I have the V of r, R-E, equals E times R-E of r. So this is great. We have a simplified equation. All the angular dependence is gone. I now have to solve this equation for the radial wave function, and then multiply it by a spherical harmonic, and I got a solution that represents a state of the system with angular momentum L and with z component of angular momentum m. The only thing I have to do, however, is to clean up this equation a little bit. And the way to clean it up is to admit that probably it's better as an equation for this product. So let's clean it up by multiplying everything by r. The r squared of little r, r-e. If I multiply by r here, I will have minus and minus plus h squared over 2m, L times L plus 1 over r squared, r, r-e, plus v of r times r-e equals e times r times r-e of r. So we'll call u of r, r times r-e of r. And look what we've got. We've got something that is has been adjusted, but things worked out to look just right. Minus h squared over 2m. The second, the r squared u of r, plus, let me open a parenthesis, v of r plus h squared over 2mr squared, L times L plus 1, u of r is equal to E times u of r. Here it is. It's just the nice form of a one-dimensional Schrödinger equation. The radial equation for the wave function dependence along R has become a radial one-dimensional particle in a potential in which it should remember two things, that this U is not quite the full radial dependence. The radial dependence is RE, which is U over R. But this equation is just very nice. And what you see is another important thing. If you look at a given particle in a potential, you have many options. You can look first for the states that have zero angular momentum, L equals 0, and you must solve this equation. Then you must look at L equals 1. There can be states with L equals 1. And then you must solve it again. And then you must solve for L equal 2, and for L equal 3, and for all values of L. So actually, yes, the three-dimensional problem is more complicated than the one-dimensional problem, but only because, in fact, solving a problem means learning how to solve it for all values of L. Now, you would imagine that if you learn how to solve it for one value of L, solving for another is not that different, and that's roughly true, but there are still differences. L equals 0 is the easiest thing. So if the particle is in 3 dimensions but has no angular momentum, and remember L equals 0 means no angular momentum. It's this case. L equals 0 means m equals 0, L squared is 0, LZ is 0. This is 0 angular momentum.